Title: How can deep neural networks fail even with global optima? This paper explores the concept of deep neural networks and their potential failures, despite achieving global optima. The authors delve into the universal approximation properties of shallow neural networks and extend these properties to any depth using a simple trick. This trick allows for the approximation of a bounded scalar-valued function by a fully connected neural network with k hidden layers, which can then be extended to a deep neural network with k plus n hidden layers. The activation functions considered include ReLU, Parametric ReLU, and Sigmoid functions. The authors demonstrate that even with global optima, deep neural networks can still fail to perform well on classification and function approximation problems. They construct examples of binary classification and function approximation in 1, 2, and high dimensions for networks with ReLU activation functions. For networks with parametric ReLU activation functions, the constructions are slightly different compared to the ReLU function. The paper also considers function approximation problems for networks with sigmoid activation functions. The paper is organized as follows. In section 2, the authors propose a simple trick to extend the expressive power of shallow neural networks to networks of any depth. The activation functions are assumed to be ReLU-like, which have a linear part for x is greater than or equal to 0, or C2 continuous with bounded second-order derivatives, such as sigmoid, tanh, soft plus, Gaussian, and RBFs. Theorem 2.1 states that if a bounded scalar-valued function f, x, can be approximated by a fully connected neural network with k hidden layers, then after attaching n extra hidden layers with any width is greater than or equal to 1, the function can still be approximated by the deep neural network with k plus n hidden layers. The authors then provide a method to construct fk plus n such that it also approximates the function f. They select one neuron at layer k plus n is greater than or equal to 1, and let its input be p1 equals epsilon fk plus c, where epsilon greater than 0 is a small enough number, and c is a constant. The inputs for other neurons at layer k plus n are set to zeros. The output of hidden layer k plus n is set to 1, a, c, epsilon a, pn, a, c, epsilon, where a, c, denotes the derivative of the activation function at point c. In sections 35, the authors construct examples of binary classification and function approximation in 1, 2, and high dimensions for networks with ReLU, parametric ReLU, and sigmoid activation functions. They demonstrate that achieving global optima does not guarantee optimal performance, as the network may still suffer from overfitting or other issues. Finally, in section 6, the authors draw conclusions about the findings presented in the paper. They emphasize the importance of understanding the properties of global optima to understand how they affect the performance of the model. The research discusses the estimation of fk plus n minus fk is less than or equal to ce, where c greater than 0 doesn't depend on e, for ReLU-like activation functions. This is achieved through Taylor's expansion and bounding the second-order derivative of the activation function. The proof involves selecting one neuron at each layer, ensuring the input remains the same as the initial condition. For unidimensional examples, a fully connected neural network with two hidden layers and a linear output neuron is considered. The cost function can be median absolute error or mean squared error. The network is designed to classify or approximate problems by dividing the interval 0, 1 into n-1 intervals. The lower bounds of the hidden layer widths are the minimal widths required for the neural networks. For binary classification, the goal is to predict labels for any given x element of 0, 1. The optimal global minimum is achieved if the width of the first hidden layer is at least 2n plus 1 and the second hidden layer is at least 2. The proof involves constructing basis functions using the ReLU activation function, reducing the number of neurons in the hidden layers, and constructing the output of the second hidden layer. The final output is a function f2, x, that achieves the optimal global minimum and correctly classifies the training set. The proposed neural network structure for 1D binary classification is illustrated in Figure 1, where the green cubes represent intermediate values. The model's weights and biases represent a global optimal solution for both mean squared error, MSE, and mean absolute error, MEI, cost functions. However, the model fails to predict any point's label if the point lies outside a small region around any xi. For the cross-entropy cost function, the final output is defined as f2, x, equals 1/2 a, I1, x, 1b1, 1/2 a, I2, x, 1b2, plus 1/2. Figure 2, d, shows f2, x, when n equals 6, b1 equals b2 equals 0.95. The authors demonstrate that the neural network can approximate a continuous function g, x, by defining a training set, xi, yi, ni equals 1, where yi equals g, xi. Ideally, f2, x, approaches g, x, pointwise as the widths of the hidden layers increase. Proposition 3.1.2 shows that if h1 is greater than or equal to n plus 2 and h2 is greater than or equal to n, there exist weights and biases such that the loss function is 0. However, for any e greater than 0 small enough, if dis, x, xi, ni equals 1, greater than e, then f2, x, equals 0, indicating poor approximation. The authors construct a neural network with two hidden layers, where the first hidden layer employs n plus 2 neurons with distinct inputs, and the second hidden layer uses n neurons. The output of the first hidden layer is used to build basis functions phi I, x, which have overlapping compact support. The final output is f2, x, equals n array summation ni equals 1 yi a, phi I, x, b, 1b, where b element of 0, 1. Proposition 3.1.3 demonstrates that even with global optima, the approximation can be very poor by adding m hidden layers with ReLU activation functions. The authors also explore the construction of deeper neural networks that can fail in unidimensional problems. Finally, they extend their approach to two-dimensional binary classification and approximation problems by defining two-dimensional basis functions based on unidimensional ones. Here is a combined summary of pages 7 and 8 of the research paper. The authors define a 2D basis function as a linear combination of unidimensional basis functions, which are used to construct a fully connected neural network for binary classification and function approximation problems. The network consists of two input neurons, 2 plus m hidden layers with ReLU activation functions, and one output neuron with a linear activation function. The authors prove that, given certain conditions on the width of the hidden layers, there exist weights and biases such that the loss function is 0 for both binary classification and function approximation problems. In the case of binary classification, the authors show that the network can learn a basis function that separates the data points into two classes. They also prove that the measure of compact support for the output function is bounded by a decreasing function of the bias term, which approaches 0 as the bias term approaches 2. In the case of function approximation, the authors show that the network can approximate a continuous function g, x, y, using a training set of uniformly distributed points in 0, 1, squared. They prove that, given certain conditions on the width of the hidden layers, there exist weights and biases such that the loss function is 0. However, they also show that the approximation will fail as the bias term approaches 2. The authors also discuss the limitations of their approach, including the fact that the size of the training set can be larger than the number of neurons, and that adding more layers does not necessarily improve the performance of the network. They also generalize their approach to high-dimensional problems, where the input is a d-dimensional hypercube, 0, 1, d, and the training set is defined as a set of uniformly distributed points in this hypercube. Overall, the authors present a novel approach to binary classification and function approximation using neural networks, and provide theoretical guarantees on the performance of their approach. However, they also highlight the limitations of their approach and identify areas for future work. The paper discusses the concept of a fully connected neural network with d input neurons, 2 plus m hidden layers employing ReLU activation functions, and one output neuron with a linear activation function. The cost function considered as either mean squared error, MSE, or mean absolute error, ME. In the context of high-dimensional binary classification, the training set xi is defined as a collection of points where yi1, i2, id equals 1 if x1, I1 less than 0.5, and y1, I2, id equals 1 if x1, I1 is greater than or equal to 0.5. The size of the training set is nd. The distance between a point x in road and the set xi x from xi is denoted as dis x, xi x. The proposition 3.3.1 states that if the first hidden layer has at least 2 decinewtons plus d neurons, the second hidden layer has at least 2 neurons, and subsequent hidden layers have at least 1 neuron, then there exist weights and biases such that the loss function is 0. Additionally, for any epsilon greater than 0 small enough, if dis x, xi x, greater than epsilon, then f2 plus m x equals 0. This is achieved by constructing a basis function, phi x, using the output of the first hidden layer and selecting appropriate sets, xj, ij, j equals 1, 2, d. The paper also presents a method to construct a function f2, x, with compact support on 0, 1, whose measure of compact support decreases to 0 as b right pointing arrow d. This function can be extended to include m extra hidden layers, resulting in f2 plus m x equals f2 x. The figures provided illustrate different scenarios for the 2D basis function, with varying xi, yj, and h values. Figure 5 shows the upper bound of the model's accuracy n2, 2b, 2, n1, 2, varying b from 1.2 to 2 and n from 50 to 10,000. These results demonstrate the relationship between the number of neurons in the first hidden layer and the model's accuracy, as well as how the choice of b affects this relationship. Here is a combined summary of pages 11 and 12. The authors explore the compact support of the model f2 plus m x in high-dimensional spaces, specifically in the context of 3D functions and image classification. Figure 6 illustrates the compact support of f2 plus m x around a specific point in 3D space, demonstrating that the d-volume of the region where the model provides positive feedback is less than 2 dB h d. Remark 3.3.1 notes that the total d-volume of this region decreases as b approaches d from d1. The authors then apply this concept to image classification, specifically binary classification of 3 by 3 pixel images into dark and light classes based on pixel grayscale values. The training set is constructed by applying a color reduction transform to each pixel, where the grayscale value p is reduced to mk, with m ranging from 2 to 5. The training set consists of 9-dimensional vectors, with each element normalized by dividing by 255. Proposition 3.3.2 establishes that for a neural network with 2 hidden layers, there exist weights and biases such that the loss function is 0, but only for images within the training set. The proof involves constructing the input for the first and second hidden layers, with the final output given by f2 plus m x. Remark 3.3.2 notes that even with a large training set, the accuracy of the constructed model is low, highlighting the limitations of the approach. The authors provide a table comparing the size of the training set and the number of neurons required for different values of m, demonstrating the enormity of the dataset and the relatively small number of neurons required. Despite this, the model still fails to achieve acceptable accuracy, even with the global optimal solution and additional hidden layers. Here is a combined summary of pages 13 and 14 of the research paper. The authors discuss high-dimensional function approximation using ReLU neural networks with 2 plus m hidden layers. They define the training set xi and the cost functions as mean squared error, MSE, or mean absolute error, ME. The authors present proposition 3.3.3, which states that if certain conditions on the number of neurons in each hidden layer are met, there exist weights and biases such that the loss function is 0. However, if the distance between the input x and the training set xi is greater than a small positive value e, the approximation is poor. The authors then introduce parametric ReLU activation functions, which are a generalization of the standard ReLU activation function. They define the basis function phi x and the function a x using the parametric ReLU activation function. These functions are used to construct the global optimal solution for fully connected deep neural networks with parametric ReLU activation functions. The authors also discuss the construction of networks with parametric ReLU activation functions, including the definition of the basis function phi, x, and the function a, x. They show how to build the optimal global solution for fully connected deep neural networks using these functions. In the unidimensional binary classification problem, the authors present proposition 4.1.1, which states that if certain conditions on the number of neurons in each hidden layer are met, there exist weights and biases such that the loss function is zero. They define the basis function phi I, x, and the linear combinations of the first hidden layer's outputs as I1, x, and I2, x. The inputs of the second hidden layer are defined, and the output of the second hidden layer is given by F2, x. The authors provide graphs of the parametric ReLU activation functions, the function q, x, and the basis function phi, x, in Figure 8. These graphs illustrate the properties of these functions and their role in constructing the optimal global solution for fully connected deep neural networks with parametric ReLU activation functions. In the context of deep neural networks, this paper explores the approximation capabilities of parametric ReLU and sigmoid activation functions. The authors construct solutions that can be as close to the global optima as possible, but the approximation is still very poor. For unidimensional binary classification problems, they show that if the first hidden layer has at least n plus 2 neurons and the second hidden layer has at least 4 neurons, there exist weights and biases such that the loss function is zero. However, for any epsilon greater than 0 small enough, if dis x, xi x greater than epsilon, then f2 plus m x equals 0, indicating a poor approximation when the target function is not 0. For unidimensional function approximation, the authors prove that if the first hidden layer has at least n plus 2 neurons, the second hidden layer has at least 2n neurons, and h2 plus k is greater than or equal to 1. 1 is less than or equal to k is less than or equal to m. There exist weights and biases such that the loss function is 0. However, for any epsilon greater than 0 small enough, if dis x, xi x greater than epsilon, then f2 plus m x equals 0, which means if g x does not equal 0, the approximation is poor. For high-dimensional problems, the authors use the same settings and notations as in section 3.3, except for the basis function and activation function. They define the basis function as an equation 3.17, requiring second neurons in the second hidden layer, each pair used to construct a, and the final output is defined in equation 4.13. As b right pointing arrow d, the approximation will fail, even though it is the global optimal solution. Deeper networks will fail in the same way as the 1D case. Finally, the authors turn to networks with sigmoid activation functions. They begin by constructing a unidimensional basis function phi, x, defined in equation 5.1, which is symmetric and tends to a spike as k increases. They then define a function a, x, in equation 5.2, which is used to construct solutions that fit the training data very well but are only good approximations near the training points xi x. The results are extended to deep networks by Theorem 2.1. Here is a combined summary of pages 17 and 18. The authors consider a fully connected neural network with 2 plus m hidden layers and one output neuron that uses a linear activation function. They aim to approximate a unidimensional function g, x, on 0, 1, by the neural network. The training set is defined as xi, yi, ni equals 1, where yi equals g, xi. Proposition 5.1.1 states that if the width of the first hidden layer is at least 2n, the width of the second hidden layer is at least n, and the width of the 2 plus k th hidden layer is at least 1, then there exist weights and biases such that the loss function is less than any given epsilon. However, if d, x, xi, ni equals 1 greater than epsilon, then the approximation is poor. The authors provide an example to illustrate this proposition, where g, x, equals sin, pi x. They construct a solution for a network with 2 hidden layers, which involves the use of basis functions phi I, x, and a linear activation function sigma, x. The resulting approximation f2, x, is shown to converge to the true function g, x, as the number of hidden layers increases. Figures 11 and 12 demonstrate the approximation f2, x, for different values of b and k, respectively. As b approaches 1 or k becomes large, the approximation worsens, and the extreme case is that the approximation is only good near the points xi, 9i equals 1. The authors also provide an example of adding extra hidden layers to the network, where they construct f2 plus m, x, using equations 5.5, 5.7. The graphs of f8, x, and f2, x, are shown to be very close to each other, and the error between them decreases as epsilon decreases. This example verifies theorem 2.1. This paper presents a new technique to extend the universal approximation of shallow neural networks to any depth. It demonstrates that with a specific choice of activation functions and weights, fully connected deep neural networks can approximate any continuous function on a compact subset of R(d). The proposed method works for vector-valued functions as well, requiring an additional hidden layer with at least v neurons, where v is the dimension of the vector-valued function. The paper also provides several examples of overfitting phenomena in fully connected deep neural networks, contradicting the common observation that the number of parameters must significantly exceed the training data size for overfitting to occur. These examples include binary classification cases and high-dimensional function approximation. In the high-dimensional function approximation section, the authors use sigmoid activation functions and show that there exist weights and biases such that for any epsilon greater than 0, the loss function is less than epsilon. However, if d, x, xi x, greater than epsilon, then f2 plus m, x, is less than or equal to epsilon, indicating poor approximation if g, x, does not equal 0. The paper references various studies on neural networks, including those on approximation capabilities, deep sparse rectifier neural networks, and optimal approximation rates for deep ReLU neural networks. It also highlights the importance of understanding the overfitting phenomenon in global optima theoretically, as well as extending the analysis to recurrent neural networks and convolutional neural networks in future work. The research paper discusses the importance of attention in neural networks, particularly in the context of sequence-to-sequence tasks. It highlights that attention mechanisms have become an essential component in various state-of-the-art models, such as the transformer model proposed by Vaswani et al. 21. This model relies solely on self-attention mechanisms, eliminating the need for convolutional or recurrent layers. The paper also delves into the approximation capabilities of deep ReLU networks, as explored by Yarotsky, 22. This work provides error bounds for approximations with deep ReLU networks, shedding light on their capacity to approximate complex functions. These findings are crucial for understanding the representational power of neural networks and their potential applications in various domains. In terms of sequence-to-sequence tasks, the transformer model has shown promising results by leveraging multi-head self-attention mechanisms. These mechanisms allow the model to attend to different representation subspaces at different positions, enabling it to capture long-range dependencies more effectively than traditional recurrent or convolutional models. The paper emphasizes that this architecture can be parallelized more easily, making it computationally efficient compared to its counterparts. Regarding the approximation capabilities of deep ReLU networks, Yarotsky's work demonstrates that these networks can approximate a wide range of functions with high accuracy. The provided error bounds offer insights into how the depth and width of the network influence its approximation capabilities, guiding researchers in designing optimal architectures for specific tasks. The paper concludes by highlighting the significance of attention mechanisms and deep ReLU networks in advancing the field of neural networks. It emphasizes the need for further research to fully understand the potential of these technologies and their applications in various areas of machine learning and artificial intelligence.